In this set of videos, we're going to solve a differential equation where we have a discontinuous forcing function. And we're going to be putting together what we've learned about the Laplace transform so far. So in these videos, we're going to be looking at an example. We're going to first describe it without any equations. So we're going to start with a spring mass system sitting at rest. Okay, so everything is in equilibrium. The force of gravity is countered by the spring force. At time t equals pi, and if a constant force is applied to the system, so we've got something pulling upwards, and this force is going to be applied until t equals 5 pi over 2, at which point the force shuts off. We want to know what happens to the system. How does it behave? We know what the solution is going to look like to begin with. It's just going to be constant at the equilibrium at 0. And we expect to see some oscillation at between pi and 5 pi over 2. But what happens once our force is removed? Okay. To put this in more formally, we're going to look at the following initial value problem. So to show that our system begins at rest, we have these initial conditions. The initial position is 0. The initial velocity is 0 also. You can see on the left-hand side here the format for an undamped spring mass system. So we're missing the first derivative term that would tell us that we have damping. And on the right-hand side, we see our forcing function. So we see that we start with no force applied to the system, so 0. And then we have a force of 1 applied from pi to 5 pi over 2, and then it shuts off again at 5 pi over 2. So we're going to use the Laplace transform to solve this problem. Okay, so our first step is going to be to rewrite our forcing function over here, which is a piecewise function, in terms of the heaviside functions that we've been working with so far. So let me remind you, we had this function definition ua of t. It was equal to 0 if t is less than a, and 1 when t is greater than a. So we think of this like a light switch, where we go from off to on at time a. Okay. If we graph our function g of t, it starts out at 0, and then at time pi, it switches on to be value 1, and then at time 3 pi over 2, we go back down to having value of 0. Okay, so we can write this function as u pi of t. So this is going to be equal to 0 up until pi when it turns on to be 1. And then we're going to be 1 until, oops, this is supposed to be 5 pi over 2. We're equal to 1 until 5 pi over 2, at which point we want to bring our value back down to 0. So I'm going to just write this out as a piecewise function just to remind you how this works. So when t is less than pi, both functions are off. Between pi and 5 pi over 2, just the first function is on. And it's equal to 1. And when t is bigger than 5 pi over 2, this looks like 1 minus 1. Both functions are on, and they cancel out to give us 0. Okay, and so we can rewrite our initial value problem in the following way. It looks like the second derivative of y plus 4y is equal to u pi of t minus u 5 pi over 2t, where our initial position is 0 and our initial velocity is also 0. Okay. Now this is in a much more compact format, and we know how to take the Laplace transform of these functions. So we're going to do that next. Okay, we're going to take the Laplace transform of each of these terms. We have that the Laplace transform of the second derivative of y, we're going to write this as s squared times y of s. This is the Laplace transform of y minus s times our initial function evaluated at 0 minus our derivative of that function at 0. So here we're incorporating our initial conditions. And I wanted to remind you that y of s is the Laplace transform of y of t. So this is the Laplace transform of our solution. If we look at the Laplace transform of 4y, we get 4 times y of s, and the Laplace transform of u pi of t, this step function, this Heaviside function, is e to the negative pi s over s, and the Laplace transform of u5 pi over 2t is the same. It's got that shifted form, e to the negative 5 pi over 2s over s. Okay, and so if we take the Laplace transform of both sides, we're left with s squared y of s plus 4y of s is equal to e to the negative pi s minus e to the negative 5 pi over 2s divided by s. Okay. Notice that our initial conditions, y of 0 and the derivative of y at 0 of little y, our solution, are both equal to 0, and that's why we only see this s squared y of s term showing up. Okay, next we're going to isolate y of s. Okay, so we have this algebraic expression. We're trying to find y of s, get it on its own, and then we're going to take the inverse Laplace transform of both sides, and this will yield our solution y of t. So we have y of s in these two places. We're going to factor out s squared plus 4. And this gives us an expression that we can work with. I'm going to just keep these exponential functions out front, and I'm going to solve for y of s. So y of s is equal to e to the negative pi s minus e to the negative 5 pi over 2s times 1 over s times 1 over s squared plus 4. So we are in good shape. We have isolated y of s. If we can just find the inverse Laplace transform of this, we have our solution. Right? Because this guy is the Laplace transform of our solution. Okay, so as is, we don't have any rules that tell us what the inverse Laplace transform of this expression should be. When we see this exponential out front, it can be helpful to use the following shift formula. It says that if you have e to the negative as times the Laplace transform of some function, f of t, this is equal to the Laplace transform of a step function, ua of t, times a shifted version. So we go from f of t to f of t minus a. What this means is we're basically starting our function, letting our function begin at a rather than at f. Okay, so the idea is that if we have these exponential parts, we're going to figure out what function gives us this as the Laplace transform of f of t. Because this means that we can, if we know this little f of t, then our solution, y of t, is going to be this shifted version of f. Okay, right now we have 1 over s times 1 over s squared plus 4, so this isn't quite written in a way where we can figure out what function it came from. So this is going to be our temporary focus, is we're going to, first, we're going to find f of t, where the Laplace transform of f of t is equal to 1 over s times 1 over s squared plus 4. Okay, so when we go to our sheet of functions and their Laplace transforms, we see that our expression 1 over s times 1 over s squared plus 4 is not on our list. So what we're going to do is use the method of partial fractions to rewrite this as a sum. So the pieces that we are going to be adding together, we're going to have a over s plus bs plus c over s squared plus 4. And we want to find the a, b, and c, so that when we add these fractions together, we get 1 over s times s squared plus 4. Okay, and one easy way to do this is to just add these fractions. So we get a times s squared plus 4 over s times s squared plus 4 plus bs squared plus cs over s times s squared plus 4. So the first term gets multiplied top and bottom by s squared plus 4. The second term gets multiplied top and bottom by s. This gives us 1 over s times s squared plus 4. Okay. We add these terms together. We find our numerators need to be equal. We have as squared plus 4a plus bs squared plus cs needs to equal 1. Okay, and that tells us that a plus b times s squared plus cs plus 4a needs to be equal to 1. So we have 3 resulting equations. A plus b is 0, c is 0, and 4a is equal to 1. So that means that A is 1/4. A and B are need to add to 0, so B is negative 1/4. And we found that C was 0. Okay, and so we find that our expression is 1/4 times 1 over s plus negative 1/4 s over s squared plus 4 is equal to the Laplace transform of f of t. Now these individual pieces we can look up in our chart. The inverse Laplace transform of 1 over s is equal to 1, and the inverse Laplace transform of s over s squared plus 4 is going to be cosine of 2t. And so by taking the inverse Laplace transform of each of these terms individually, we find that this function f of t is going to be 1/4 minus 1/4 cosine of 2t. Okay, and let's back up to the problem that we were trying to solve. Okay, so I wanted to remind you of what we did to get here before we finish up this problem. So we had our initial value problem. We took the Laplace transform both sides, and then we solved for the Laplace transform of our solution. So this is y of s. We were able to write it as some exponential terms times the rational part. And we have a shift formula that says that if you have an exponential times the Laplace transform of some function you know, then this is the Laplace transform of just a shifted version of that function f. So we set out to find the function f of t, whose Laplace transform was this rational part. We used the partial fraction decomposition to rewrite it as a sum. And we were able to work out what f of t had to be by using our inverse Laplace transform. Okay, and so now we are in good shape to apply this shift formula. We have exponentials times the Laplace transform of a function we know. So our answer is going to be just shifted versions of this function f of t. Okay. So first off, we're going to be looking at this term e to the negative pi s times the Laplace transform of f. And so y of t, our actual solution, is going to be u to the pi of t, f of t minus pi, because in this example, a is equal to pi. In the next exponential term, this coefficient is 5 pi over 2. So here, a is equal to 5 pi over 2. And so we're going to apply the same formula. So we have the Heaviside function, where we change from 0 to 1 at 5 pi over 2, times the shifted version f of t minus 5 pi over 2, the shifted version of f. Okay, now let's fill in what our function f is equal to. F was 1/4 minus 1/4 cosine of 2t, so it's going to be 1/4 minus 1/4 cosine of 2t. Cosine of 2 times t minus pi. Okay, so what did we do here? Every time we see a t in this expression for f of t, we're going to be replacing it with t minus pi. So we have cosine of 2t, this becomes cosine of 2 times t minus pi. So we're just doing that composition really carefully. In the next version, every time we see a t, we're going to replace it with t minus 5 pi over 2. So we have 1/4 minus 1/4 cosine of 2 times t minus 5 pi over 2. Okay, and at this point, we can call it done. But when we look at this, we might be like, oh, what's going on here? It's a little hard to tell, right? So I think it can be helpful to, let's rewrite this in terms of a piecewise function. I'm going to start here on the left, and we're going to do some simplifications along the way. The first part is really easy. Neither of these functions are on until after time pi. So we're equal to 0 if t is less than pi. Okay. Then at time pi, this first function turns on, and so our output is going to be 1/4 minus 1/4 cosine of 2t minus 2 pi. So our first function has turned on. I've just distributed the 2 in. So this is for t bigger than pi and less than 5 pi over 2. Okay, next up, at time 5 pi over 2, our second function turns on also. And so we're going to be taking the difference of these two functions. So let's write that out. Okay, and so we have this, this difference when t is greater than 5 pi over 2. We can see a little bit of simplification can be done. We have a 1/4 and a minus 1/4. So these guys are going to cancel away. And then the other thing that we can do to simplify is to look at these shifted cosines and write them just in terms of cosine. So we know that if we take cosine of x, it's equal to cosine of x plus 2 pi, right? Because the period of cosine is 2 pi. Okay. So here where we have, whenever we have a whole number multiple of 2 pi, we can just drop that term. Okay. What that means for us is we're going to be able to drop this 2 pi here and here. And this 5 pi, we're going to be able to change into just a pi. So we drop 4 pi basically from this expression. And the second thing that we can notice is that if we have cosine of x minus pi, this is shifting the cosine graph to the right by pi. This is just equal to negative cosine of x. So, the second term can be just replaced with negative cosine of 2t. Okay, so let me rewrite this function, our solution. Okay, so our solution is going to be equal to 0 from 0 to pi. Then it's going to look like 1/4 minus 1/4 cosine of 2t. And just doing a little bit of simplification in the bottom, we're replacing that cosine function with negative cosine of 2t. And we see we've got 3 negative signs. So we have just two copies of -1/4 cosine of 2t added together. And so we can actually replace this entire second term, or third term, I guess, with -1/2 cosine of 2t. And we can make some basic observations here. Our system starts out at rest. Then we're going to have just we have a force applied to the system, and so our position is always just going to be positive when we have this applied force. And then the force is removed, and our system continues to oscillate for all time. Okay. Next up, we're going to try graphing these functions just to see what our solutions look like. Okay, so altogether, this is our solution function. Let's graph this thing. So it starts off easy. Our function is equal to 0 to begin with. Our position function is 0. Then between pi and 5 pi over 2, we've got this form 1/4 minus 1/4 cosine of 2t. So the middle of the wave here is going to be up at 1/4, and our amplitude is going to be 1/4. So the height of the wave is 1/4. That means that pi is the lowest point on this wave. So a quick reminder: this guy tells you the middle of the wave. And our amplitude comes from the coefficient in front of the cosine. And we see that we're going through the cosine function twice as fast as usual, so our period is just pi. And a quick reminder, you can calculate this by calculating 2 pi divided by this coefficient inside of the cosine. Okay, so here's our midline. We said that the height of our wave is 1/4, so our lowest point is here at pi, and we complete one entire period in pi. So what does this look like? We've got our maximum here at 1/2. And this is going to continue on until 5 pi over 2. This is halfway. This is only half of a period, and so we're going to be stopping here at the maximum. Okay, at 5 pi over 2, our function turns and becomes -1/2 cosine of 2t. This function has a midline of 0. Midline is y equals 0. Our amplitude here is 1/2, so our waves have height 1/2. And our period stays the same, just pi. And so now our amplitude is twice as big as it was before. We finish one complete period in length in pi. And so we're going to go all the way down to -1/2, since our midline is now at 0. Oops, it's a little rough on the tablet. Okay, and we're going to continue oscillating in this way forever. And so there you have it. This is what our solutions look like. In this problem, we saw that we stopped applying the force at 5 pi over 2 when the mass was at the maximum possible height. If we had changed the time that we stopped applying force, we changed what the solution ends, like how it ends. So, for example, if we were to stop it at 3 pi rather than at 5 pi over 2, this would be exactly enough to just cancel out all of the action. So the resulting, the behavior after we stop applying the force, and in particular its amplitude, depends on when we where the mass is when we stop forcing.